Hi, my name is Brad Morrow, and I'm a student in Dr. Wu's Image Processing and Computer Vision course at the University of Florida. This is a presentation of my course project, which is a neural network implementation of digit recognition using backpropagation. There are several different applications for digit recognition, like a post office could use digit recognition trying to recognize zip codes on letters. A mobile device could use digit recognition to take input from the touchpad and turn that into data. Or you can also use it for scanning handwritten documents. Several different machine learning techniques have been used to address this problem, one being neural networks, like this project covers, but also linear classifiers and nearest neighbor classifiers are a couple other examples. Most other algorithms for digit recognition require you to explicitly extract features, unlike the neural network. Neural networks borrow from the theory of the human nervous system. Synapse weights are developed many times initially randomly and then refined over iterations until they can adequately calculate the correct output based on true outputs given to the system. In this case, our input data is an image. You can do it with one layer. It could be as simple as using the weights to multiply by an input to determine the output directly, or you can add what are called hidden layers in the middle, and it's just multiple layers of matrix multiplication in the middle to come up with your output. There's a couple different ways you can update your synapse weights in the forward direction, and that's different than what I did here. I used the backpropagation method where I calculated an output and then backed the synapse weights back up from the last layer to the front. The project was developed in Python using the Anaconda development environment. Python was a new language for me. That was one of the first tasks, was to build some skill with the new syntax. Used data files from the mixed National Institute of Standards and Technology database, MNIST database, which is a mixture of handwritten digits from census workers and high school students that had some pre-processing performed on them. As a second task, I also had a few colleagues from work handwrite some digits, and I individually cropped those out and used those as input to test it with some less controlled data input. I used the spider development environment inside of Anaconda. Actually tried a few others prior and either didn't get much stability in the ability to run my program, or had a little more trouble importing some of the packages. My functions in my Python code do three different types of functions. One is processing the data from the initial source. For the MNIST, there are data files that contain all of the image pixels for 60,000, 10,000 images, and they're in a specific order. So some of the functions take data out of those files and pull them into a format that I can use for the neural network. In the case of my personal images, I fit them in the same formatting. Training the neural network is the main function. That's using the training images to develop the synapse weights. And then the last few functions were testing, and that's using different images, either the MNIST testing images or the images from my colleagues, to determine what the error rate of the network was. Training consisted of a few steps. First, I randomly initialized weights between -1 and 1, and then over iterations refined those. Calculated the output classifications using the current weights, which were not very accurate at the beginning but got better over time. You compare the results of your calculation to the true labels, and then you apply corrections, like I said, in the backward direction, and iterated many thousands of times, as many as 200,000 in the last case. That took several hours to execute that at that number of iterations, waiting for the weights to converge and be able to get an acceptable error rate on the handwritten digits. As I mentioned, I used 60,000 MNIST training images, and I used 10,000 testing images from that database. Had 3 hidden layers in the final implementation, and each hidden layer had 16 nodes. 200,000 training iterations was the maximum that I ran it at. And the best error rate I achieved was 12.9% on the MNIST data. And that's compared to some other 3-layer neural networks have achieved rates of 2 to 3% based on the literature. And other algorithms have achieved less than 1% up to 12% in a search of the literature. And using a small number of testing images from the colleague database achieved a 30% error rate, which I thought was impressively close to the 12.9, considering how few images were used and also how much less controlled the pre-processing was. For those tests, I used the same parameters mentioned above for MNIST. A few things became clear early in the process. I started off with only 1 hidden layer, and that didn't get as good of an error rate as what I wound up with. And each hidden layer that I added, the second and the third, incrementally improved the performance, assuming the same values of the other parameters. And I also had to optimize the number of nodes in each hidden layer. I tried fewer and more, but 16 nodes per layer wound up being optimal. I tried uneven numbers of nodes, and really the 16 in each layer gave the best performance of anything I used. And the other concept is that the convergence of the algorithm depends a little bit on what I call a tuning parameter, because it behaves a little bit like a proportional controller, in that it can overshoot and then ring down to the correct value. So that I considered the amount that I divided the additions to the synapse weights to be like a tuning parameter, and the value of that worked the best was just the number of rows times the columns, which is the number of pixels in these images. There were 28 by 28 pixel images. And if I used less than that, it would take many more iterations to accomplish the goal of reducing the error rate. If I used any more gain than that, it would go unstable. Now I'll do a walkthrough of my code and also run the code and let you see it. It trains, and then it runs the testing on both sets of testing data at once. So let's come over. Okay. Here on the left side, if you can see, is the code, and on the right side here, this is in Anaconda Spider development environment. So first I'll start the code, get it started over here on the right. I'll show you something over here, and then we'll move back to the left and talk about the functions more. It takes a few seconds to wind up. Okay, I just wanted to show what this was. This just prints out the number of the iteration that's currently being performed in the training phase. And then below here is just for one particular training image what the calculated output is. And I used that to determine how fast it was converging, or whether it was stable, or whether it's heading towards the correct number that I know that image should be, which in this case was a 3, so it's already pretty close. Okay, up here on the top left, I imported a few packages. I use the image package and NumPy. My first two functions here are display image, and those aren't used in the calculation of error rate. That was mainly for troubleshooting the code, making sure I had the correct way of bringing an image into my system. What it would do is just go into the input file, get all the pixels for one image, and then show the image on the screen to show that I had it oriented correctly, or that I actually had a number. The next two down here, array train labels, array test labels. It took the file that contained the labels, which are the correct output values for each digit, and it put them into an array, or in Python called a list. That actually I took it into a list and then made an array out of it, but it's for the optimal multiplication when I'm actually performing the neural network calculations. Then I have array train images, array test images, similar to the labels. It's right here. Similar to the labels, it went into the input files from MNIST. It got the pixel information, the values, put them in the correct spot for the multiplication. The format of the matrix that's used here for the inputs is each row is an entire image, and there's number of images times of number of rows in the matrix. And the reason for that is that the shape of the image doesn't really matter to the neural network. It just needs to know pixel 28, pixel 29, no matter whether that's on the right hand side or the left hand side of the next row. So array train images, array test images, pulls in the data into my input. And then array colleague test images is similar. It's for the manual images that were created, and the difference is that there's not a single file that gets opened with all the data pulled in. They're individually bitmap files for each cropped photo, and then same process is performed, just putting the pixels in one long row. And over here, since they were written in black on white background, and the MNIST data was in a negative so that the writing was in white or a lighter gray, that's what the 255 minus value here does, is it negates the image. So here's, I pulled in all the data for that testing. Here's the train function right here, and that does the main part of this algorithm. It runs array train images and array train labels to pull in the data into the right format. It seeds a random number generator, and the reason for that is to be predictable, one run to the next, so you can debug your code. Then initializing the synapse weights to random values between -1 and 1. All of the values in this multiplication were between -1 and 1. Even the pixel values that are normally 0 to 255 were normalized to 0 to 1. Here's where you input the number of, let's see if I can highlight it here. That's where you input the number of iterations that you're going to run on training. In this case it's 2,000, and that's what I ran on the code I just ran, just for time's sake. As I mentioned, the larger numbers could take well longer than the amount of time for this video. Here are the first values of the layers, L0 through L3. And each row it uses a sigmoid function, which you know that the value of that will always be -1 to 1. So you know that you're in the right range for multiplication here. You apply that to a dot product of your layer value times that synapse in matrix format. So you do that for each of the 3 layers. Here's just the printing that shows what you saw over there. Compare what you got for level 3 to the correct output as determined by the array input, and then you scale that value and start going backwards through adjusting your synapses from level 3, level 2, level 1, and here you're updating the synapse value by multiplying your calculated level 0 by that delta function that you came up with that's based on error. You update synapse 1, 2, 0, 1, and 2, and over here this divided by rows times columns is where I was talking about a tuning factor. If I used much higher than that, it would go unstable. In most cases, if I used much less than that, it would take a lot longer to converge. Training check is a function it's basically a testing function on the training data that was just used to train. So I'll show you actually what the test functions did, and you'll know that that's what training check does just with the original training data. That was for setting up the code. Test, all it does is it pulls in input as array test images and output as array test labels, which is very similar to what you just saw in train, but using the different data. And then it just calculates level 0, level 1, level 2, level 3 forward through the neural network to get a level 3 output, same as you did in the training. It scales it to be on the same scale as the Y value for the output, and then it rounds because I want that to be just a whole number to compare. You know, if the neural network produced a number of 3.12, I turn that into 3 because that's the closest value to what it got, and then I compare that to see if the correct value was 3 or not. Okay, to set up a counter of errors, I go through and look how many are different and increment the error counter, and then divide by the number of test images to see what the error rate is and print it out. Same thing was done for test colleague, except just like with the input, I had to use manual Y values. There's no data file to go pull those out of. I had to write down what the correct values were. So I used array colleague test images and then manually entered the Y's here. And did the same thing as you saw in the last one, printed an error rate. And that leaves the main function as, one second, guess I'm at the bottom. The main function here at the bottom trains and then uses the test colleague and test functions using the parameters that come out of the train function to put into the test. And over on the right hand side you see that it finished 2,000 iterations. These were the calculated values for the colleague test. It got a 40% error rate for the colleague error rate, and it got 26.3% for the MNIST error rate. And that's not as good as the final values, but that's because not as many iterations were used as I used when I ran it for a couple hours. So that's the essence of the code. I also wanted to show you, this is an example, very much blown up, of one of the colleague images. Now it was written on a piece of paper and then it was scanned in, turned into a bitmap, but then it was compressed down to 28 by 28 pixels to match the formatting of the other data. Okay, we're back. Now let's talk about some of the lessons learned during this project. And one was that training neural networks is time and processing intensive. Like I said, it took many iterations that even with a fairly powerful PC took several hours to complete, and really had to wait for those iterations to get the error rates to converge at a lower value. This task would be ideally suited to a general purpose GPU, but I just used a PC for mine. The other thing is that tuning the synapse value updates is critical, meaning the scaling of each update to the synapse for each individual calculation. Like I said before, if I used too much gain, it would only take a few hundred iterations before I'd be bouncing between 1 and 0 and wouldn't get anything out. And then if I made too small of adjustments, it would take much longer to converge.